IOE 413 Nonlinear Programming Study Guide.
This question asks whether the problem that you see here is a convex programming problem or not. So the first thing we need to do is determine whether the objective function is convex or not. Look at f of x. So to do that, we need to evaluate the Hessian. And to do that, we need to compute some partial derivatives. So let's look at the partial derivative with respect to x1. That's 2x1. And then the second partial derivative of f with respect to x1 and then x2, and that's 0. And then the second partial derivative of f of x with respect to x1 is 2. Let's go over here and look at the partial derivative of f with respect to x2. And that's 2x2. The second partial derivative of f with respect to x2 and then x1, that's just equal to 0. And the second partial derivative of f with respect to x2 is 2. Let's take the partial derivatives that we just computed and make the Hessian. It is a 2 by 2 symmetric matrix, 2, 0, 0, 2. Notice that x does not appear in here anywhere. It's just a matrix of constants. Recall that for a symmetric 2 by 2 matrix, A, B, B, C, the conditions for it being positive semi-definite are that A is non-negative, C is non-negative, and AC minus B squared is non-negative. So let's check to see if those three conditions hold for our Hessian matrix here, 2, 0, 0, 2. Well, A is 2. That's non-negative. C is 2. That's non-negative. AC minus B squared is 2 times 2 minus 0 squared. So that's 4. That's non-negative. So our three conditions for our matrix to be positive semi-definite here, that one is satisfied, that one is satisfied, and that one is satisfied. Therefore, h of x is PSD everywhere. And therefore, f of x is convex. Everywhere. We have just shown that the objective function is convex. What we need to do now is show that the set of all x that satisfies these conditions is also convex, and then we'll be done. So let's look at each one of these conditions here in the constraint set. Recall from the lecture notes that theorem NLP1 said that a half space is convex. And notice that this is a half space. So the set of x satisfying that is convex. Let's look at the constraints down here. x1, x2 is greater than or equal to 0. The first one, x1 greater than or equal to 0, can be written as x1 plus 0, x2 is greater than or equal to 0. And that's a half space. So that's also convex. And then we can write down 0x1 plus x2 is greater than or equal to 0. And that's a half space, so that's also convex. Now, let's look at this equality for a moment. and break it into two inequalities. x1 plus x2 is less than or equal to 2. And x1 plus x2 is greater than or equal to 2. These two inequalities define the exact same set of x's that satisfy these two as an equality. Right? You have an equality and split it up into two inequalities of different directions, and it's exactly the same thing. Well, notice this first one, x1 plus x2 is less than or equal to 2, is a half space, so it's convex. x1 plus x2 is greater than or equal to 2 is a half space, so it's convex. Now, by theorem NLP2 in the lecture notes, we know that an intersection of convex sets that are non-empty is convex. So we have a whole bunch of convex sets here, and the intersection of these convex sets defines the feasible region for this problem. And this theorem NLP2 says that if you take an intersection of these convex sets, it will be convex. Therefore, the set of all x satisfying these conditions is convex. So now we have shown that the objective function is convex and the feasible region is convex, so we have a convex programming problem.